So now that we have a strategy for finding the local classification of critical points, we find critical points by figuring out where the gradient vector vanishes, and then we can classify those critical points as local maximum or local minimum or saddle based on this second derivative test that uses the x and y pure partial derivatives multiplied together minus the mixed partial derivative squared. Right? That quantity called the discriminant, when it's positive, tells me that all the concavities agree, so I have either a local max or min. When it's negative, I know that some of the concavities disagree with one another, so I must have a saddle. When it's equal to 0, we call it a singular critical point or a degenerate critical point, and then we have to do something totally different. We can't use the second derivative test. It's inconclusive. So if that answers the local maximum and minimum question, what about the absolute maximum and minimum question? And so how do we figure out where a function reaches a global max and a global min? And the answer to that question requires us to specify a domain for the function, especially if that domain is something that's less than, smaller than, is a proper subset of its natural maximal domain. And so an example of a kind of question that we might run into is something like this. Suppose that my inputs, x and y, have to live inside of some closed region, some what we call a compact domain. So it's closed and it's bounded. So it's a bounded region, and we also include the boundary, the edge of that region, as part of our domain of interest. And the question might be, I have some function of two variables. How do I find out the largest and smallest, absolute largest and smallest values that the function attains on this closed domain? So not just for any x and y, but just for those x's and y's that live within a domain like this one. So for the purposes of this example, let's take this closed domain to be this ellipse. So x squared plus 16y squared is less than or equal to 16 is a way to describe this shaded region. So that includes the interior that's shaded in blue, and it also includes the boundary curve that's shaded here in black. Now the good news is that if what we're trying to do is find the global maximum and minimum of any continuous function, we only require that it be continuous, it will attain a global maximum and a global minimum value on any compact domain. So any closed and bounded subset of the xy plane, in this case, a continuous function will have a global maximum and global minimum value. So it's not going to be a fool's errand. We're not going to be chasing after something that doesn't exist, as long as my function is continuous and the domain on which we're optimizing it is closed and bounded. But then it's another question of how to actually find those things. So the function that I want to consider here is the one whose formula I put up here, 4 minus x squared minus y squared plus 2x plus 4y. And so the idea is something like this. Whatever the graph of this function might look like, we sort of think about, zoom out on this a little bit here, we think about taking these xy values that are within just that domain and sort of looking at projecting that domain up onto the graph itself in 3 dimensions. If I do that, hide this for a second. So as I'm looking at this from above, I'm just seeing that boundary curve there. But when I look at it in 3 dimensions, we can see that that boundary curve is tracing out this sort of boomerang, Nike swoosh shaped kind of shape on this graph. And so somewhere it's reaching its highest possible z-value. Somewhere it's reaching its lowest possible z-value. Right? And it looks to me like the lowest possible z-value is probably right about there. And so our job is going to be to figure out how to find those largest and smallest possible z-values that are being attained by the function on this compact domain. And so the first things that we would probably want to look for is, are there any critical points of my function? Are there any actual local minimum and maximum points inside of my domain? In this example, just based on the graph, it looks like the answer is no. But again, that depends on the region that we chose. If I chose a slightly bigger region, like maybe I expand this one out a little bit. Oops. So if I chose a bigger region, I might find that the interior of my region does contain an actual local maximum or minimum. Like, so come back to this one here. So now it looks like my region is large enough. Oops. My region is large enough so that this top of the mountain that I'm seeing right here is actually inside of my region. And so there it would be valid to include that critical point of my function as part of the analysis. But we already know how to find those local minimum and maximum points, so let's focus on the ones that we don't yet have tools to find, which are maximum and minimum values that occur along the boundary of one of my regions, right? One of our edge cases. How might we be able to do that? So typically the strategy is something like this. I'm going to go over to my other place to type over here. So if I want to find the max and min of a function along the boundary of a compact closed bounded region. So this is the thing that we want to try to do. Then the first thing I probably am going to do is come up with some way of describing just the boundary of my region, just those x and y values which are a part of the boundary, right? Just a part of this black curve here, which is the outside of my ellipse in this example. And the most straightforward way to do that is to parameterize the boundary. So come up with a vector valued function that describes the boundary of my region in 2 dimensions. So I'm going to try to keep track here in a way that we can kind of see as much as we can. So how do I do that? I'll just move this. So if I want to parameterize the boundary curve in this example, my boundary curve is the ellipse that has a semi-major axis of 4 and a semi-minor axis of 1, right? It goes out to 4, 0 in the x direction and 0, 1 in the y direction. And so I can parameterize that ellipse with a vector valued function that I can get just by taking the equation of a circle and stretching the circle by a factor of 4, stretching the unit circle on a factor of 4 just in the x direction. So I can use like cosine t, sine t parameterization, but multiply the cosine t part by a 4. So that would be a parameterization of the boundary of this ellipse. And what's nice about that is that that describes for me every single xy point that is a part of that boundary. And as long as I let t range from 0 to 2 pi, that gives me the whole unit circle, remember, it's going to give me the whole ellipse going all the way around this side. So there is my parameterization. And so if I then take just those xy values, just the xy values that we can obtain by plugging a value of the parameter t into this parameterization, if I plug just those values into my function f, then what I'm going to get is a parametric curve in 3-dimensional space that resides on the surface of my graph. So let me see if I can drag this up into view here. It doesn't want to let me do that. Zoom out on this a little bit. So if I were to take just those xy values and plug them into my function, I'm going to get the z coordinates at every single point along my boundary curve. And once I have those z coordinates, I'm going to have a single variable function that's going to take my parameter as input, and it's going to spit out the z value of a point on this 3-dimensional curve, my boundary curve projected up onto my graph surface in 3 dimensions. Then I just need to find the maximum and minimum value of that single variable function. So what I'm saying, after we parameterize the boundary, we'll just evaluate the function that we're trying to find maximum and minimum for, called the objective function, on the boundary curve. So using the parametric curve, using this parameterization as input with an n. So again, in other words, all I'm going to do is replace x in my function with 4 cosine of t, and then replace y with sine of t. So I'm just going to find f of r of t. And since my function was, get my equation for this here, 4 minus x squared minus y squared plus 2x plus 4y, I'm just going to put in place of all my x's 4 cosine t's. And in place of all my y's, I'm going to put sine t. So now that I evaluated my function using the parameterization as input, now I have a function that only depends on the single variable t. Let's simplify this out as much as we can here. So 4 minus 4 cosine squared of t, minus 16 cosine squared of t, minus sine squared of t, plus 8 cosine t, plus 4 sine t. So we could maybe do a little bit of work to try to simplify this if we want to. We could just take one of these cosine squared of t's and peel it off from this 16 so that I have 15 of them, negative 15 of them, and an additional negative 1 of them. If I do that, I end up with this cosine squared t and sine squared t with the same sign, sign, on them. I factor out that minus that's in front of both of them, just so that we have an opportunity here to simplify just in one step by using the Pythagorean identity. Cosine squared of t plus sine squared of t is equal to 1. So I'll just replace that quantity by a 1. That makes it a like term with the 4 that's out here in the front. So my simplified version of f of r of t is this expression, 3 minus 15 cosine squared t plus 8 cosine t plus 4 sine t. And that is the value, the z value, of the points along my boundary curve inside 3 dimensions, all the z coordinates. So now that I have that expression, find the absolute max and min of this single variable function, just using ordinary single variable calculus optimization strategies. So if I'm using single variable calculus optimization strategy, then I'm just going to take this f of r of t, this function, and find its critical points. Critical points of f of r of t. And according to single variable calculus, I just need to find where the derivative, ordinary derivative, is equal to 0. And so now it just becomes the kind of optimization problem that you could have done in first semester calculus. So the derivative of f of r of t, just need to take the derivative with respect to t of this function that we're looking at above us. So 3 is a constant, so its derivative is 0. Minus 15 cosine squared of t, its derivative is going to be positive 15 sine t cosine t, using the chain rule there. Plus 8 cosine t, its derivative will be minus 8 sine t, and then plus 4 sine t, its derivative is going to be 4 cosine t. And so I need to figure out, if I can, where is that equal to 0? Which t values is that equal to 0? Unfortunately, I don't know if we can solve this particular trigonometric equation analytically. I have to think harder about that. There may be some clever way to do this that I'm not seeing. So since this is a challenging equation to solve analytically, if we solve it using numerical or graphical methods, I would just graph this function, right? And I'm looking for where this function, this derivative, is equal to 0. And there's, turns out, 4 different places on the interval from 0 to 2 pi where this function becomes 0. One of them right here at t equals 1.334, another one here, another one here, another one here. So it gives me these 4 different t values. T equals 1.334, 3.247, 5.028, and 6.099. And so then once I have found those t values, those are going to be the places that are the candidates for the absolute maximum and minimum points of the function along this curve. And so then we would just want to evaluate what is the z value at each of those points. So find the largest and smallest z values from among the critical points. Right, in the usual single variable calculus type of strategy. So I'll just find what is f of r of each of those. 1.334. because these are nasty numbers also, we'll just use a little bit of technology to help us out with this too. So my f function was 3 minus 15 times cosine squared of t plus 8 cosine of t plus 4 sine of t. And so in the blue here is the graph of the z-values themselves, and in the black, those are the derivatives. So those are the ones that I'm using to try to find my maximum and minimum values. And so here are my largest z-value and smallest z-value from among all of the points that we would be interested in here. Looks like there's one right here also, and one right there. So when I plug all of these in, the largest z-value from among these is the one found at t equals 1.334, which is about 7.94, is the largest, and f of r of 3.247. Sorry, I'll scroll up on this a little bit so you can see it in my screen. F of 3.247, which is approximately negative 20.21, is least. And so those would be the maximum and minimum, global maximum and minimum values for this function on the domain of question. And we can kind of see on this graph that the minimum point having a y value of about negative 20 seems about right. It's pretty far down on that z-axis. And the largest value being about 7.94, that also appears to line up with where the top of that swoosh shape that we drew on the surface lines up. So that's the main strategy for if we're trying to find the maximum and minimum values on a compact domain. The first thing we would do is parameterize the boundary of the domain. So it's going to give us this expression for x and y in terms of a parameter t. Then we just stuff that parameterized curve into my function to get a single variable function that tells me the z-values of all the points on the boundary of that region, and then use standard single variable calculus strategies to find the absolute max and min of that single variable function. This one was hard to do analytically just because my boundary was elliptical, so the cosines and sines gave us a challenging single variable calculus problem to do. But if you were to follow in the textbook the last example, the activity number 6 in this section, that particular one is set up to be a little bit more manageable in some ways. So for this one, you're optimizing, sorry, let me transition over here. You're optimizing a function on a triangular region. So x plus y is less than or equal to 4, and x and y are both greater than or equal to 0. So that triangular region in the xy plane. And so when you parameterize the boundary, you end up needing to do 3 different parameterization. A parameterization for the horizontal side, a parameterization for the diagonal side, and another parameterization for the vertical side. Each of those parameterizations is significantly simpler than the one that we just did, but you do have to do them in 3 separate steps. So if you want a good example of what a problem like this can look like, activity number 6 in this section is a good place to start.